everyone. I am Vineet Kumar Sinha from ABES Engineering College, Kasyapa. In this video lecture series, we are discussing the subject Materials Engineering, and right now we are discussing Unit 5, that is Non-Destructive Testing. And the today's topic of discussion is Eddy current testing. So as per the syllabus, we'll cover in this video 2-3 testing methods, non-destructive testing techniques. First one is eddy current testing. Second is radiography, and third one is X-ray diffraction. Coming on to eddy current testing, it is used to detect surface flaws. Only surface flaws can be detected, and to measure thin walls also. Thin walls and surface flaws from one surface only. To measure thin coating in some application, to measure depth. Thin depth of the coating can also be measured. This method is applicable to electrically conductive materials. The limitation is it can be applicable to electrically conductive materials only. In this method, eddy currents are produced in the product by bringing it close to an alternating current carrying coil. The product of which the testing is to be done we have to bring it close to an alternating current carrying coil to generate eddy currents inside it. The main application of the eddy current technique are for the detection of surface or subsurface flaws, conductivity measurement, and coating thickness measurement. Applications of ECT is crack detection, corrosion monitoring, material thickness measurement, coating thickness measurements, and conductivity measurements. What are the advantages of ECT? It is sensitive to small cracks and other defects. It detects surface and near surface defects. Inspection gives immediate results. Equipment is very portable and easily can be handled. Method can be used for much more than flaw detection and inspects complex shapes and size of conductive material also. But what are the limitations? Only conductive materials can be inspected. Skill and training required is more extensive than other techniques. Skill and training required. Surface finish and roughness may interfere of the surface finish of the surface, and roughness may interfere with the result, and also depth of penetration is limited. Coming on to the next non-NDT technique is radiography. So radiography testing, RT or industrial radiography, NDT, method of inspecting material for hidden flaws. This radiography is for hidden flaws, inside flaws that the depth also we can have done by this radiography by using the ability of short wavelength electromagnetic radiation. The electromagnetic radiation required is short wavelength X-rays or gamma rays, high energy photons to penetrate various materials. Radiography testing method is nothing but to take the shadow picture of an object onto a film by the passage of X-ray or gamma ray through it. It is the same as the medical radiography, X-ray, as we all know. When we go, if we have some bones problem or any ailment where X-rays are required, that is medical radiography. And similarly, industrial radiography is used where X-ray as well as gamma rays are used for detection. Only difference in their wavelength. That the difference between X-ray and gamma rays is it's the only difference in their wavelength. So radiography testing process, we can see this is the radiation source, and if this is the specimen, this is complete is the specimen, and there is a flaw inside this portion. So we'll apply a film over here, and this exposed to this radiation source, and this will create a image like this, and the flaw will be seen here inside. Here also the radiography generator, and suppose there is a crack inside this surface. or there is a pore inside the surface, there's a channel inside surface, and hole inside the surface. This can be projected here in X-ray film. After development is like this. The crack will be seen like this. The pore will be seen like this. And the channel, we can assess the channel. Where is the channel and how much is the length and width of it. And also the hole, the size of the hole can be ascertained on the film. Difference between X-ray and gamma ray radiography. What is the difference between these two? The X-rays are having larger wavelengths, while gamma rays are having shorter wavelength. X-rays are having less penetrating power. Gamma rays are having high penetrating power. X-rays are used for components having thickness up to 62 mm only because penetration power is less, and it is used for more thickness components due to high penetrating power. Only one component can be examined at a time, and where in gamma rays, many components can be examined at a time while making it stack. Equipment is larger in size. Here the X-ray equipment is larger and gamma rays equipment is very portable and smaller in size. It is more intensity and faster application and faster process. The gamma ray processes, gamma ray radiography is less intensity and slower. This is the comparison between X-ray and gamma rays. Here we can see that if a crack is present over there in a material in the body, in a wheel, it can be detected as a crack here in the radiographic film. Limitation of radiography, it's possible health hazard. It's injurious to health, and exposure to X-rays or gamma rays is very injurious to health, and it poses health hazard. It's need to direct the beam accurately for two-dimensional defects. The direction of application of beam for two-dimensional defects is very critical to analyze the real size of the defect, or the size of the damage, or the interpretation of results. Film processing and viewing facilities are necessary. The development of film processing and viewing facilities are also required to know or to have the results measured. Not suitable for automation. It is not suitable for automation process, and also not suitable for surface defects. It is only for hidden flaws or inside depth flaws. Applications of radiography for detection of internal defects. It is applied for detection of internal defects, for detection of porosity, casting, lack of fusion in welding, and cracks, for measurement of geometry variation and thickness of components. Also, we can see this normal image of a torch, and here the radiographic image is showing there is a gap inside. Coming on to next technique, this is X-ray diffraction. So X-rays, what are X-rays? X-rays were discovered by Wilhelm Röntgen, who called them X-rays because the nature at first was unknown. So X-rays are also called Röntgen rays. X-ray diffraction in crystal was discovered by Max von Laue. The wavelength range is 0.01 to about 10 nanometers. X-rays are short wavelength electromagnetic radiation, as discussed before, produced by the deceleration of high energy electrons or by electronic transition of electrons in the inner orbital of atoms. Jumping of an electron creates X-rays. The penetrating power of X-ray depends on energy also. There are two types of X-rays: hard X-rays, which have high frequency and have more energy, and soft X-rays, which have comparatively less penetrating power and have low energy. The X-ray diffraction method in non-destructive testing, we can say that X-ray diffraction is a powerful analytical technique used to study the crystallographic structure of material. In NDT, XRD or X-ray diffraction is employed for analyzing residual stresses, phase identification, and texture analysis of the material, and also grain size determination. The how exactly it works, or how it is the principle of X-ray diffraction. So X-ray diffraction is based on constructive interference of monochromatic X-ray. An incident beam is placed on the surface to be detected. So there would be a reflection angle diffracted beam would be there, and diffraction beam is recorded. And there would be a transmitted beam, and in any crystalline material. So the diffraction, constructive diffraction or constructive interference will cause this 2 theta. There would be a change in a 2 theta of the angle diffraction, and it will be calculated on that diffraction pattern would be recorded. So X-ray diffraction is based on constructive interference, of monochromatic X-rays and a crystalline sample. These X-rays are generated by a cathode ray tube filtered to produce monochromatic radiation, collimated to concentrate and directed towards the sample. The interaction of incident rays with the same produce constructive interference when conditions satisfy Bragg's law. So as per Bragg's law, or when the conditions satisfy Bragg's law, the constructive interference happens and the diffracted beam gets recorded. Principle of X-ray diffraction is based on Bragg's law, which describes the relationship between the angle of incidence, wavelength of X-rays, and interatomic spacing in a crystal lattice. As per the relation, n lambda equals to 2d sine theta, where n is the order of diffraction, lambda is the wavelength, d is the interplanar spacing, and theta is the diffraction angle. So diffraction pattern, when X-rays interact with the crystalline material, they are diffracted at specific angles, producing a diffraction pattern. Each peak in the diffraction pattern corresponds to a specific crystal plane spacing and lattice orientation. Here we can see this is wave 1. This is wave 1. And this is wave 2. Impinging on the material and having the wavelength lambda, one complete wave from this point to this point. This is lambda. And having an incident angle of theta. Then the reflected angle would also be theta. And similarly for wave 1 also, incident angle is theta and reflected angle is theta. So, and here also the wavelength is lambda. But now the extra distance which this wave has to move is this much. This is d sine theta. This distance as well as this distance. So this is the extra distance for which this wave has to move. If atomic plane distance is d, as mentioned here, atomic plane distance is d, then this can be calculated. This theta and d can be compared when this is for the case n equals to 2. Similarly, other planes also n equals to 3, 4, 5, and it is calculated as per the relation n lambda equals to 2d sine theta given by Bragg's law. So applications of X-ray diffraction in NDT, it can be used for residue stress analysis, phase identification, texture analysis, grain size determination. All these are the application of X-ray diffraction in NDT. The instrumentation used for X-ray diffraction are X-ray source, this is important, detector, and also goniometer. Advantage of X-ray diffraction in NDT, it is non-destructive. X-ray is non-destructive. XRD allowing analysis of materials without altering their integrity. High sensitivity, XRD can detect small changes in crystal structure, making it highly sensitive to material variation. And also wide applicability, it can analyze a wide range of materials including metals, ceramic, polymers, and composites. What are the limitation of X-ray diffraction? The sample preparation must be properly prepared, otherwise often requiring grinding or polishing to expose the flat surface for analysis. Complexity, instrumental analysis can be complex, requiring trained personnel. Limited penetration, X-rays have limited penetration depth in dense materials. So at the conclusion, X-ray diffraction is a versatile NDT method that offers valuable insights into material structure and properties. With proper instrumentation analysis technique, XRD plays a crucial role in ensuring the quality and integrity of engineering materials in various industries. So this was all for this video. In the next video, we'll discuss the latter topics. Thank you.